There are attractive forces between solute particles that hold them together. We've talked about this before, how in an ionic bond, the positive sodium ion is attracted to the negative chloride ion, and that's what holds those ions together in that ionic crystal. But there is also interactions between solvent molecules, specifically water, since we're dealing with aqueous solutions here. So water is polar, meaning that one side is partially positive and one side is partially negative. And so water molecules are attracted to other water molecules because of this, but water molecules are also attracted to other charged particles like ions. When we mix the solute with the solvent, there are attractive particles between everything. There are attractive particles between the solvent and the solute. There's attractive particles solute to solute, and there's attractive particles solvent to solvent. If the attractions between the solute and the solvent are strong enough, the solute will dissolve. So again, in a water molecule, there's an uneven distribution of electrons. This causes the oxygen end to be partially negative and the hydrogen end to be partially positive. You may have seen it drawn more like this than the space-filling model there. Those S's just indicate a partial charge, like a 0.5 charge instead of a +1 or a +2 or -1. It's a +0.5. So when sodium chloride is put into water, the attraction of the sodium ions and the chloride ions to water molecules competes with the attraction between the sodium ions and the chloride ions themselves. And in the case of a soluble compound like sodium chloride, what ends up happening is the attraction between the water molecule and the ion is stronger than the attraction of the ions for each other. And so the water molecules will actually come in, they will pluck the ions off of the crystal, and they will surround them, as in this image here. So the attractive forces that are holding that crystal together, the attraction between the positive ion and the negative ion, is overcome by the attraction between water molecules and the ion. And you can see there, it will pull off an ion and surround it with water molecules, and it just keeps doing that one at a time until the entire crystal has been broken apart. So when ionic compounds dissolve, they break up into individual ions. So when sodium chloride dissolves, it's actually present as not as a crystal, but as sodium ions and chloride ions that are surrounded by water molecules. So we can show this with a little reaction, breaks up into sodium ions and chloride ions. When calcium chloride breaks up, for every calcium chloride, there's one calcium ion, but there are two chloride ions, and so you have to indicate that as 2Cl-. So this 2 became that 2. I missed one. So we're going to give the concentration of all of the ions in a 0.5 molar solution of cobalt-2 nitrate. So as cobalt-2 nitrate dissociates, we will get 1 cobalt ion and 2 nitrate ions. And then we're basically just using the balanced chemical reaction, just like we did with stoichiometry. If this is 0.5 moles, for every cobalt-2 nitrate, I get 1 cobalt, so it's a 1-to-1 ratio. So the cobalt is 0.5 molar. And then for every 1 cobalt-2 nitrate, I get 2 nitrate ions, so I get twice as much. And so you multiply the concentration by 2. It's the same as if we had actually done the stoichiometry. 1 cobalt-2 nitrate and 2 nitrates. And so that's where I got the 1.0 molar from. We're going to say how many moles of silver ions are present in 25 milliliters of a 0.75 molar, that should be Ag2SO4 solution. So the first thing you always want to do with these types of problems is show it splitting up into ions. I have 25 milliliters of a 0.75 molar solution, and it's asking me to find moles of silver. So based on what I'm given, I know that my equation is going to be the molarity formula, moles over liters. So I have 0.75 molar equals X over 25 milliliters is 0.025 liters. So X is going to be 0.01875 moles. And this was 25 milliliters of a 0.75 molar silver sulfate solution. So what I just solved for was moles of silver sulfate. And then doing the same thing that we did on the last slide, using my balanced reaction, for every 1 mole of silver sulfate, I get 2 moles of silver ions. So it's going to be 0.0375 mole. I can only have 2 sig figs, so 0.038 mole of silver ions. Not ionic, all ionic compounds dissolve in water. Some are what is called insoluble. Silver chloride is an example of an insoluble compound. And the reason for this is just those attractions. The attractions between the silver ions and the chloride ions are stronger than the attraction of either ion for water. So water is not able to come in and pull that ion apart the way it is in a soluble compound. So soluble means it dissolves in water. And that means that the state of this in a chemical reaction is going to be aqueous. Insoluble means it does not dissolve in water, so the state in a chemical reaction will be solid. So it's important to know your solubility rules. So this top box here are soluble things, and then the bottom is insoluble things. And so you see for the first 2 rows there, lithium, sodium, potassium, ammonium, nitrate, and acetate, there are no exceptions. Those are always soluble. Chlorides, bromides, iodides, almost always soluble. 2 exceptions, silver or lead-2. And then sulfate has quite a few exceptions. On the bottom there with the insoluble compounds, hydroxide is usually insoluble. An exception to that would be calcium. Calcium makes hydroxide soluble. And then cobalt, sulfides, and phosphates are always insoluble. So going through some examples here, these are on the next slide, but I'm going to just do them here. We'll start with copper 2 chloride. So here's chlorides. Chlorides are typically soluble. If I check the exceptions, copper is not one of them. So that's going to be soluble. Lead 2 chloride. Lead is an exception to chloride. So what that means is lead is an exception to the solubility of chloride. So when chloride is with lead 2, it's insoluble. Calcium nitrate. Nitrates are always soluble. So that one's soluble. Barium sulfate. Sulfates are typically soluble, but let's check the exceptions. Barium's an exception, so that makes it insoluble. Lithium carbonate. Now this is a tricky one because lithium's in the soluble with no exceptions. Carbonate's in the insoluble with no exceptions. So soluble is greater than insoluble. If something is soluble, that takes precedence over something else being insoluble. So lithium carbonate, because lithium is soluble, that whole compound is soluble. So lithium, sodium, potassium, ammonium, nitrates, acetates are 1,000,000% of the time soluble. It does not matter what they are bonded with because soluble always takes precedent over insoluble. So then same thing with the ammonium hydroxide. Ammonium's up here insoluble, hydroxide's down here in insoluble, but soluble always takes precedence. So ammonium hydroxide is soluble. So we just did those. Let's talk about precipitation reactions. A precipitation reaction is a reaction in which a solid, called a precipitate, forms when we mix two solutions. So you have two aqueous reactants. In this case, we have our lead iodide and our potassium iodide and our lead nitrate. When those are mixed, they form a solid yellow lead iodide precipitate. So as you can see there, it's not a big chunk of solid. It's kind of little tiny particles of solid, but it is a bright yellow precipitate that's pretty easy to see. So precipitation reactions do not always occur when two solutions are mixed. When we did reactions before, we said, well, let's just say for now that double replacement reactions go, but they in fact don't always. If you have two soluble compounds, so let's say I'm just writing what's on the picture bigger. So potassium iodide plus sodium chloride, when those rearrange, we're going to get sodium iodide and potassium chloride. And if I look at my solubility rules and I look at the states of those products, they are both soluble. So both products are aqueous. And so no reaction really occurs because no solid product forms. I started with a bunch of ions. I'm ending with a bunch of ions. There's no change overall in my reaction because no solid product forms. So a double replacement reaction will only occur if one of your products is solid. So that's what this says here. For a precipitation reaction to occur, one of the products must be insoluble. So we're going to write an equation for the reaction that occurs when potassium carbonate and nickel 2 chloride are mixed. So that's going to form potassium chloride, which is aqueous, soluble. Again, let me write that. Soluble means aqueous. Insoluble means solid. So we're going to get potassium chloride and we're going to get nickel carbonate. Carbonates are typically insoluble, so there is going to be a solid product there. So since I have a solid product, this reaction does occur. I have to just finish it by balancing it by putting a 2 in front of the potassium chloride. So sodium nitrate and lithium sulfate. So I'm going to get sodium sulfate. Sodiums are always soluble, so that's going to be aqueous. And lithium nitrate. Nitrates and lithiums are always soluble, so that one's aqueous. So since I have two aqueous products, I don't have a solid product that forms. This is actually going to be no reaction. You have to have a solid product to have a reaction.